Seems like we're going to be accompanied by the drums. All right, so if we're just thinking about the Bohr model for the moment, and let's consider, we just represent the nucleus like that as a hole in the middle, and when we are putting electrons in that an element might have, so in time we look at the periodic table, we just pick an element, let's just say it's sodium. So for sodium that has 11 electrons, because it's got an atomic number of 11, that means that the element has 11 electrons as well, then that would mean for our Bohr model that our electrons are in the closest shells as they can possibly be to the nucleus. Okay, I wouldn't, if I then drew another orbital around here and just say I move that outer electron up there, then that sodium would be in an excited state. So we have to have an understanding of ground state and excited state. Just like when you're excited and you're high energy, when the electrons are excited, they are also high energy. The ground state means that all the electrons are as close to the nucleus as they can possibly be. And we know that the electrons move between energy levels by absorbing or emitting packets of energy which we call photons. Now, this isn't in the course, but de Broglie did postulate that the electron has properties of a particle and a wave. And the wave-particle duality is something that's more considered in physics than in chemistry. We know that we can see light behave, and electrons behave in that way. Yeah, that's been confirmed experimentally. Now Schrödinger was the one who took this understanding from Niels Bohr and refined it in a way that actually explained what we could see in the spectra. And so the spectra were used to work backwards to the explanation. And in actual fact, it's about probabilities. It's whereas we should be able to know where the electrons are in Niels Bohr's model, we don't ever know where they are. There's the Heisenberg uncertainty principle that means that we can't know the direction it's travelling and where it is at the same time. And so Schrödinger set up an equation that determined the actual configuration of the orbitals. We don't have to worry about his calculations, but we are interested in occupied orbitals. Because in essence there are an infinite number of orbitals that the electron could be in, just getting further and further away from the nucleus, but we want to look at the ones where electrons are actually sitting at the time. And what we're going to introduce here is principal quantum number. And it's handy for us, if I bring this back down again, that the principal quantum number actually actually matches up with periods. So principal quantum number 1, 2, 3, 4, 5 as we go down the periodic table. And we'll look to see why that's the case as we move on. But we don't have these orbitals. What we actually have are these are our orbitals. The orbitals that where our valence electrons are positioned, P, D and F, S, this is the S block, P over here, D in the middle, and the F down here for the lanthanides and actinides. Some students like to write S, P, D and F on their periodic table on your formula sheets until you get a handle of these labels. They come from the spectra as well. That's why they've got random names. It's not like 1, 2, 3, 4 or A, B, C, D. This was sharp. That was the lines that came out on the spectrum were sharp, diffuse for these ones, and so that's where these letters come from. You don't need to worry about why they're called that. You just need to be able to use S, P, D and F. We don't actually use F though, in that the elements down here are there's so many electrons that we would have to consider that really, if you can show your understanding up here, then it's a waste of time to try and get you to do it down there. Okay, so we now have S, P, D and F orbitals. Not like this one here, closest to the nucleus, is actually a spherical shape. These, the p orbitals, they're like dumbbells. And D are also a bit like dumbbells. And F are a bit more complex. If you think about it, if you're trying to pack electrons around a nucleus as efficiently as you can, putting them in ever-growing circles is not efficient. Okay, if you're blowing up a balloon and you're putting a bigger and bigger balloon around the nucleus, the area within each of them is increasing all the time. And so that's why the electrons aren't going into ever-increasing spheres. That they do, but they do other things as well. So our S's are spheres. Our p orbitals, though, and if we think of this as x, y, and z normally, so it's trying to represent 3 dimensions, the p orbitals are dumbbells along each of those axes. So if you think that we would have had electrons in a sphere in the middle, and then we can put electrons into our dumbbells. Now, there's another rule here that we can only put 2 electrons in each orbital. So this spherical orbital can hold a maximum of 2, as can each of these dumbbells hold a maximum of 2, and every orbital can hold a maximum of 2 electrons. And so that's one of the reasons why in Phys Sci we were drawing those electrons in pairs, because they do actually hang around by and large in pairs. That part is true. Now, our electrons are all negatively charged, and trying to put two negatively charged particles in the same orbital means that they will repel each other, won't they? And the way they overcome this repulsion is there's the Pauli exclusion principle here, that we need to have, you know how if you have a moving charge you can induce electricity, and you, so that's sort of like physics, isn't it? Have you done that sort of thing where you've done any No? Okay. So for our electrons that both have the same charge to be able to exist next to each other, what we have to do is have one spin one way and the other spin the other way. And so they minimize the repulsion that they feel to each other. And that's another reason why I guess there's a maximum of 2 in there. You couldn't put in another one without upsetting that balance. This gives them a little bit of stability by having opposite poles with their spin in opposite directions. And so the way we represent that, if we're thinking about our electron configuration, is like that. So each of these is an electron spin, but the arrow points up and the arrow points down to indicate that they have opposite spins in the same orbital. Okay, so let's then use that to think about principal quantum number 1. There's one orbital that can, and it's an s orbital, and it can hold a maximum of 2 electrons. It's closest to the nucleus. Then principal quantum number 2 also has an s orbital that also holds a maximum of 2 electrons, and it is further away from the nucleus. They are both spheres. Then after that, then we have the p orbitals, and there are 3 of them, the 3 dumbbells along the x, y, and z axes. They're at a slightly higher energy level, and they can hold, there's 3, they can hold 2 each, so that's a maximum of 6 electrons. When we go up to 3s2 is our next one, and again it can hold 2 electrons. 3p6, same again. And we'll just stop there for the moment, because what I want to do is look, well, how can I talk about electron configurations for an element? Let's think firstly, remember sodium has 11 electrons. And so for the ground state for sodium, I'm going to have 2 electrons in that 1s orbital. I'm going to have 2 electrons in my 2s orbital. I'm going to have this completely filled, the 2p, 6 is completely filled, and then I have 1 electron in the 3s, don't I? 6, 7, 8, 9, 10. That's 11 electrons. So how would I write out my electron configuration for sodium now? It's like that. I'm going to say how many electrons I have in each of my orbitals. My little numbers up the top here, they all have to add up to 11. Because there are 11 electrons, for sodium has 11 electrons. The S and the P, these are the orbitals. And the big numbers out the front, these are the principal quantum numbers. Tell us how many electrons can be in that level. Now it's principal, not principal. So this word here means primary or most important. You know, like the principal of the school is the most important person in the hierarchy of the school. This here is my morals. You know, like, do I believe in, I don't know, smoking in public or giving alcohol to children or something like that? That's my principles. So please don't write principal quantum number with an LE. It's the most important. Now you might also see this sometimes arranged as boxes as well. I've just made them as lines, but they can also be boxes like that. The next thing I want to talk to you about would be, let's have a look at a different element. Maybe we'll do silicon, that's 14. Okay, so silicon is 14. I'm going to do this whole process again. This time I'm going to ask you to think more about the process of filling, because I didn't do that carefully last time. 14. First the electron goes in closest to the nucleus. Second electron goes in closest to the nucleus with the opposite spin. Third electron goes into the next closest orbital, which is the 2s orbital, and the fourth electron goes in with it because, again, it's closest to the nucleus and therefore it has to go in with the opposite spin. We've got 4 electrons in, we've got 10 to go. The fifth electron goes into this orbital here, into the first p orbital, but the 6th electron goes into the next empty orbital because it's more stable for the electron to be by itself than it is to be paired up. It's still preferable to be by itself like that. The next one, again, goes into the next empty orbital because these are all at the same energy level. Now when I come back with my 8th electron, now I'm starting to double up. So now I have to go back in and put in an electron with the opposite spin in and fill an orbital. And that process continues. 4, 6, 8, 10, 11, 12, because that's the same, remember, and I'll just make these ones. So how many electrons have we got? 2, 4, 6, 8, 10, 12. We've got 2 more to go. 13, 14. So if I were to write out then the electron configuration for silicon, 1s2, 2s2, 2p6, 3s2, 3p2. So I only have 2 electrons in that p orbital, in the 2p orbitals there. We might just stop there for a moment and we'll come back and have a bit more and look at this after lunch.